Now see here, next topic, reflection on the basis of wave theory. Suppose you have taken here, this is a mirror. Here this is have taken a large plane mirror. Now a plane wave front AB incident over here, that is A and B, and these are the rays to the wave front which are actually perpendicular to the wave front. So these rays are perpendicular to the wave front. When this ray strikes at this point, this is angle of incidence, and this will be reflected to this side. This is angle of reflection here, that is R. Now no need to make here this R here, just we can draw this one. Now according to Huygens principle, every point of the plane wavefront or every point of the wavefront act as a new source of radiation. So this point is acting as a new source of radiation and giving out radiation in all direction, but the radiation are reflected in the same plane to this side, and the one radiation I have taken to this side here. And at the same point B is also emitting the radiation, and these radiations suppose travel to this side, and it has taken time to travel to the A dash. Suppose the time is t, so the distance travelled is here, that is c into t. So we can write d, that is equal to B A dash is equal to c into t. Suppose radiation coming from B has taken time t to reach to the point A dash. So by taking the radius B A dash, a spherical wavefront is drawn. Similarly, because this is in this vacuum and this radiation is also going in vacuum. So by taking the radius point A also and radius equal to B A dash, that means c into t, another spherical wavefront is drawn. So suppose by taking the center B and radius B A dash, tangent is obtained over here, and here by taking the center as A, and suppose that is a c into t, we will cut an arc like that c into t. We get here and join these two tangents, you will be getting here another wavefront. So this one is called here the reflected wavefront. So AB is incident wavefront and A dash B dash is the reflected wavefront, and these rays goes like this, and we can make also in this way. This one is also 90. This whole thing we can take as I, and this we can take as R. Now here in triangle A dash B A dash, in triangle A dash B A, we can write sin I is equal to A dash B upon A dash, and then we can write A dash B is a perpendicular, A dash is hypotenuse here, that is here C into T upon A dash. Similarly, we can write in triangle A B dash A dash. So triangle A B dash A dash, we can write sin R is equal to A B dash upon A dash is equal to C into T upon A dash. Now if we look at these two angles sin and sin R, these two are equal. So we can write here basically sin I is equal to sin R, or we can write I is equal to R. It means angle of incidence is equal to angle of reflection. Yeah. And also that thing is that the incident plane wavefront and the reflected plane wavefront all lie in the same plane. So by this way we can justify laws of reflection of light on the basis of the wave theory. So this is actually the laws of reflection. Now see a refraction on the basis of wave theory. Here suppose you have taken, this is the interface of the medium, that is x and y, and here is rarer medium this side, and here I have taken that is a denser medium, any medium where light can travel, that is here. Suppose there is a plane wavefront like this, A and B is incidenting over here. We can write this one is one ray and another one is this ray. This is strike at this point, this is the normal, this is angle of incidence. According to Huygens principle, every point of this wavefront acts as a new source of disturbances. So, point A is acting as a new source of disturbances. So, it sends out radiation in all directions. So, we will see here the radiation which are going into the medium, suppose they are traveling like this. This will be here, here angle of refraction r, and also from here the radiation which are emitted from here travels here in the straight line. This point is taken as A dash, this is I, and this also goes to this side, that is R. Now, this radiation B A dash, suppose the light has taken time t to travel from B to A dash. So, we can write here B A dash is equal to actually C into t, because the speed of light in vacuum or in air is, that is a c. So, the distance travelled B A dash in time t is equal to C into t, but the radiation which is coming into here at the same time, that will travel different distance in time interval t. Suppose this is travelling the distance here, suppose this is here, we can take v into t, because the speed of light in the medium is v. So, by taking the B as a center and radius B A dash, a wave front is drawn here, and similarly by taking A as a center, a spherical wave front is drawn, and whose point is this, and this tangent is joined here. So, now we will be getting here, this is B dash, this thing is considered angle of incidence I, and this is considered angle of refraction R. So, this is incident plane wavefront and this is refracted plane wavefront. Now, we can take triangle, in triangle A dash B A, we can write sin I is equal to A dash B upon A dash, that is C into T upon A dash. Similarly, we can write in triangle here A dash B dash A, these are the 90 degree here. We can write sin R is equal to, in this case, AB dash upon here AA dash. Now, AB dash is equal to V into T. So, we can write V into T upon AA dash. Now, if you have got this sin I and sin R, you divide these two, you will be getting sin I upon sin R, that is equal to C into T upon AA dash into V into T upon AA dash. Cancel this and this. You will be getting sin I upon sin R is equal to C upon V is equal to mu 2 1. That is the refractive index of the second medium with respect to first. So, this is actually known as here Snell's law. So, we have derived Snell's law by using wave theory. So, this is the explanation of the refraction of light on the basis of the wave theory. So, first law is only this one is here, the sin I upon sin R is equal to mu, that is the relative refractive index, and also the here now the incident plane wave front and reflected plane wave front all lie in the same plane.